Two prime numbers p and q satisfy the equation p plus q is 31. What is pq? P plus q is 31, so let's see here. The smallest prime number is 2. That would mean this would have to be a 29, and 29 is indeed a prime number. So p is 2, q is 29. So therefore p times q would be 2 times 29, and that is 58. The integer 203 has an odd ones digit, an even tens digit, and an even hundreds digit. How many integers between 100 and 999 have an odd ones digit, an even tens digit, and an even hundreds digit? We have a 3-digit number, and it's between 100 and 999. So this, and this we have to figure out. Okay, the first one, which they are calling the hundreds digit, they're saying it's even. So it's going to be either 2, 4, 6, or 8. It can't be 0, even though 0 is an even digit, believe it or not. But it can't be 0 because that would make that number no longer be 3 digits. And also it would fall outside of the range. The second digit, they're calling a tens digit, and that's got to be even also. But this can be a 0. So it can be 0, 2, 4, 6, or 8. And then the last digit is the ones digit, and that they're saying is odd. So that's going to be 1, 3, 5, 7, or 9. So 4 choices here, these guys. 5 choices here, these guys, and these 5 choices here. So the total would be 4 times 5 times 5, and that is 100. The distance from point P to O is 17. The distance from point P to A is also 17. What are the two possible pairs of coordinates x, y for P? Let's draw a little coordinate grid. So we've got 0 to P, and they're saying that's 17. And then we also have P down to A is also 17. Okay, and A is given as 16, 0. So I'm going to draw a line that's perpendicular to the x-axis, and that will cut A, that's 16 in half. So this will be 8 and 8. And this is, of course, the y-coordinate of P. So using basic Pythagorean theorem, you can get that y squared plus 8 squared is equal to 17 squared. And therefore y is plus or minus 15. So therefore my point P has two choices. It's either 8, 15, or it's 8 minus 15. A store sells shirts, water bottles, and chocolate bars. Shirts cost $10, water $5, and chocolate $1. On a particular day, the store sold X shirts, Y water bottles, and Z chocolate bars. The total revenue is $120. X, Y, and Z are integers, with X, Y, and Z greater than 0. How many possibilities are there for the order triple X, Y, Z? So the equation that we would create with the information in the question is 120 is equal to 10x plus 5y plus z. If I put the 10x and the 5y on one side, then what I can do at this point is factor out of 5. And if I factor out of 5, I will get 5 is equal to 5 times 24 minus 2x minus y is z. So that means that z is basically equal to 5 times something. So I can say that z is equal to 5t, let's say. And if that is the case, then I can put that back into here. So it'll be 120 is equal to 10x plus 5y plus z, but I'm calling it 5t since I'm confident that it's a multiple of 5. And then we'll divide through the whole thing by 5, and that'll be 24 is equal to 2x plus y plus t. Now at this point, I can get sort of a better understanding of what x, y, and z could be. So let's make a table, x, y, and t actually, and then z is just equal to 5t, which is what I've set it as. Okay, and then for every value of t, I'll get one value for z. Okay, so all three of them are greater than 0, so let's start with the smallest number that's greater than 0, the smallest integer, and that's 1. So if x is 1, and I plug it into there, I'll get 22 is equal to y plus t. And since y is an integer, and z is an integer, and t is an integer, I only need to look at integer values. So that means my y and t could be 1 and 21, 2 and 20, and so on down all the way till 1 and 21. Yeah. Okay, so that would actually mean that that's 21 ordered triples, because each of these t's is going to give one value for z. So it's going to be the same amount. So these are all ones, by the way. X is all one. So that's 21. Now let's talk about x equals 2. When x equals 2, this equation now becomes 20 is equal to y plus t. So that's going to be 1 and 19, 2 and 18, and then all the way down to 19 and 1. And therefore that is 19. And remember, these are all 2's for the value of x. And so on. So when x is 3, you're going to get 17 ordered triples. When x is 4, you're going to get 15, and so on down. 5 will give you 13, 6 will give you 11, 7 for x will give you 9, 8 will give you 7, 9 will give you 5, 10 will give you 3, and finally 11 for x will give you just 1 ordered triple. And then now to get the total, I guess we just have to add up all these numbers. 1 plus 3 plus 5 plus 7 all the way up to 21. And when you do, you get a grand total of 121. What are all pairs of integers Rp for which r squared minus r times p plus 6 plus p squared plus 5p plus 6 is equal to 0? Let us arrange this in a way that makes it look like a quadratic equation. So let me do this carefully here. R plus p squared plus 5p plus 6. Okay, so that I purposely put it in that form because I want it to look like ax squared plus bx plus c equals 0. You guys are a little bit more familiar with that, right? And this is a quadratic, and you may remember something called the discriminant. And discriminant of an equation of that form is b squared minus 4ac. And for a quadratic equation to have real solutions, it has to have a discriminant that is greater than or equal to 0. Because if the discriminant was less than 0, it would not be real solutions, it would be imaginary. And they want integer. They actually want integer solutions. So this definitely has to be greater than or equal to 0. So in this equation, what is my a, b, c? My a looks to me like 1. My b looks like this negative p plus 6. And the c is that whole big long thing, p squared plus 5p plus 6. So let's calculate the discriminant. Let's call it d for discriminant. So b squared minus 4ac would be minus p plus 6 all squared minus 4ac plus 5p plus 6. Got it? Okay, so let's expand this. So this will be p squared plus 12p plus 36 minus 4p squared minus 20p minus 24. And if I collect like terms, it'll be minus 3p squared minus 8p plus 12. And this has to be greater than or equal to 0. Okay. If that is greater than or equal to 0, we have to think about this for a second. So, for example, if I were to plot that function, you would have 2 points that cross the x-axis, and then of course it would open downwards. So I have to figure out what those 2 points are, and then I can figure out what is the range for p for that expression to be greater than 0. And unfortunately, to figure out those 2 points, I've got to set this equal to 0 and do a quadratic again. So let's do that. So p this time would be minus b plus or minus the square root of b squared minus 4ac all over 2a. And then this is 8 plus or minus root 208 over minus 6. And if you get out a calculator, you'll figure out that there's 3.7 and 1.1 approximately. So that means that if this is, say, 1.1 and this is minus 3.7 right here, let's say, then that means it kind of behaves like this, like that. That's what the parabola, because the parabola is going to open down because that is a negative in front of that p squared. So what we are interested in is really this region right here. When is that parabola greater than 0? And it's between that region. So it's basically between 1.1 and minus 3.7. Now p is an integer. See, it's an integer, these guys. So that means p is going to be either -3, -2, -1, 0, or 1. Got it? But we want to figure out r as well, because we have to figure out r and p. So then we are going to use this guy to figure out r, that original equation. So let's put that original equation in the screen here. So it's r squared minus r times p plus 6 plus p squared plus 5p plus 6 is 0. And let's figure out r for each of these. So for p equals -3, p equals -2, p equals -1, p equals 0, and p equals 1. Okay, here we go. So when p equals -3, we're subbing that into this guy. So we will get r squared minus 3r plus 9 minus 15 plus 6. And that's r squared minus 3r. And that is r times 3 minus r. And that equals 0, right? Yeah, it equals 0. So that basically means that r is equal to either 0 or 3. And then since that was for p equals -3, our pairs are 0, -3, and 3, -3. So we got two pairs so far. And we just keep going like that. So when p is -2, again, we sub it in to this guy right here, and we will get r squared minus 4r is 0. So that means r times r minus 4 is 0. So therefore r is either 0 or 4. So that means we have 0 minus 2 or 0, 4, I believe. Is that right? 0 minus 2 and oh, hold on. I think I messed this up. Oh, sorry. 0 minus 2 and 4 minus 2. Yeah, I got to make sure I do that properly. Okay, that's good. And then when p is -1, and we sub it into there, we will get r squared minus 5r plus 2. And that actually has no integer solutions. And you can check that by doing a quadratic. If p equals 0, we sub that and we get r squared minus 6r plus 6, and that also has no integer solutions. If p equals +1, we will get r squared minus 7r plus 12 is 0. That actually factors to r minus 3, and r minus 4 is 0, and therefore r would be 3 and 4, and therefore we have 3, 1, and 4, 1 as our final pairs. So these 6 pairs are the solutions to that original equation up here. Cube ABCDEFG has edge length 6 and P is on BG, so that BP equals PG. What is the volume of the three-dimensional region that lies both inside both square-based pyramid EFGHP and square-based pyramid ABCD? So they've already told you that the base is a square, and that's very helpful, I think. So let's proceed with a side view of ABGF. So a side view of ABGF. That I will draw on a coordinate grid like this. So here we go. So this is A, this is B, G, and F. And what I'm trying to do is trying to figure out where do they intersect. And what I'm particularly referring to is the lines AG and PF. Where do they intersect? And then later I'll discuss where is the intersection of lines G, C, and PH. And then we might talk about GD and PE. And those pretty much would define the boundaries of the base, square base, the square base that they're talking about for the top pyramid and the bottom pyramid, because it's essentially two pyramids that are joined at one common base, which is a square. Okay, so from A to G is this line segment, A to G, and then P is halfway, right? So this is, P is where? About approximately here. Yeah, that's about halfway. So that would be like that. So this, I'll just call that X. That is the intersection point. Now to get that intersection point, we're going to need to label all of these in terms of the coordinates. So I'll call that 0, 0. This will be 6, 0, since the edge length is 6. This will be 6, 6. And then this would be 0, 6. And then since P is halfway, BP is equal to PG, that'll be 6, 3. Okay, so the line from FP, that slope you can easily figure out is a half, and therefore the equation will be x over 2. The line from A to G, that slope you can easily figure out is minus 1, and therefore that line would be minus x plus 6. To get the intersection point x, you set this equal to this, and you'll get x over 2 is equal to minus x plus 6, and when you solve for that, you'll get x equal to 4, and therefore y will be equal to 2 when you sub it back in. So therefore that is a 4, 2 point. So that means this top to bottom height is 2 from the base, the absolute base of that cube to x, which is the intersection point of AG and PF. This is that intersection of those two lines. Okay, that's actually very good progress. In a very similarly, you can show that PH and GC, these two guys, also intersect 2 above the base. Intersect at a height. I should have squeezed that in there. Yeah, intersect at a height 2 above the base. And what that allows us to do is get an idea of how this shape is going to look now. This shape, the region, is basically a square base, and you're going to have sort of a pyramid like that. That's the top pyramid, and then there's going to be a similar pyramid that goes downward. Now this first one that I drew, it's going to have the points P, the X, and then a few others, right? But the P we know already is 6, 3. The X we just calculated was 4, 2. So this point here, that point is very important. Now the base is square, and it's flat. It's sort of parallel to this base right here, the base of this shape, I guess. So it would be the intersection point of AG and PF, which is right here, and then the intersection point of GC and PH. So GC and PH. So GC, PH. So right here. Let me just see if I can draw this red dot here. That dot right there. And then the intersection point of GC and PH. So GC and PH is here. And then finally the intersection point of GD and PE. GD and PE. So here. So it's kind of like this. Like that. So do you see that? Hopefully that makes sense. That is a square base. And it's very good that they even said that. They've told you it's a square, that base. And it's parallel to the base at the bottom. Now we need to know the side length of that base. The side length of the big base is 6, but we need to know the side length of that little guy. Hopefully you can see that it's two pyramids. One that opens up. The one that opens up, I'll just sort of shade it in green, and the one that opens down, I'll just shade it in yellow. Right, like that. And they both share that square base. Now the square base which I kind of drew here, I need to know the side length. And that can be figured out because that point that I just drew there, I'm drawing it in yellow now, that is on the same plane as x, this point right here. So therefore it would have the same y coordinate. So since the y coordinate of x is 2, it would have the same y coordinate. Now it would have the same x coordinate as P because it is on, it's basically here. It's right here. So it would be 6. So let me draw in on this graph that red line represents sort of this line here from x to that point. So therefore that looks to me like you're going from 4 to 6, so that's 2. So it's a 2, 2, 2 squared. So it's a 2, 2, 2, 2 squared. Okay, now we can figure out the volume of that region. So we have the top pyramid and then the bottom pyramid. All right, so here we go. The volume would be 1/3 the area of the base times the height. And the bottom pyramid would be, again, 1/3 times the area of the base times the height of that pyramid. Well, the area of the base, this is the base right here. That's a square with side length 2, so that's just 2 times 2. The height of the top pyramid, okay, that one, let me see if I can use green. That's this height here, that little green line I drew, from the base all the way up to P. So we are going up, let's see here, 2 to 3. We're going from 2 to 3, so that's a increment of 1. So that's 1 there. So that's 1. And then 1/3 area of the base is also the same base, so it's again a 2 by 2, but this height is the distance, I'll do it in red this time, from the base down to the floor. And that is going from 2 down to 0 this time. So that's 2 for the height. So this looks like to me like a half times 4 plus a, that should be a third. Sorry about that. 1/3 times 4 plus 1/3 times 8. And that is going to be 1/3 times 12. And that is 4.